We got to know how we went from a totally flooded globe to the current topography and geography. Then I'm going to talk about huge erosion during this runoff. When the water is moving off, it forms flat surfaces called planation surfaces, and it erodes the rocks and pulverizes the soft rocks, and the resistant rocks get carried far. And I'm going to go into this. I'm going to go into water and wind gaps are cut during the channelized phase, and then I'm going to talk about pediments are smooth. And, oh no, this is a messed up PowerPoint. I've recently changed computers, changed to PowerPoint 2010 from 2002, and the seventh topic is submarine canyons. It is off the bottom. Incompatibilities. And I'm still computer challenged, by the way. It seems like I'm always 20 years behind with all this new technology. My kids, one son-in-law is a computer programmer, and the other son is a computer programmer, and my youngest son is great at it, so they know probably 1,000 times as much as I do about computers. But anyway, when we're talking about these issues, challenges in the earth science, and there's hundreds of challenges. We have good answers for many of these challenges. But anyway, when I'm challenged, I hold fast to the Bible. 1 Thessalonians 5:21 is my theme verse for research. Examine everything carefully, hold fast to that which is good. I'm holding fast to the Bible as God's accurate word to us. And from there, I'm going to examine everything carefully. So I'm back to this diagram that I introduced last night. This is from Taz Walker. He divides the flood up into two major stages. The flooding stage, in which the waters flooded the earth, and at day 150 it peaked. And then they started to recede off, and I'll go into this more. Now, during the flooding stage, I believe that's when practically all the sedimentary rocks in the continents were laid down and the fossils in there. And the retreating stage was mainly an erosional stage on the continents. And you can divide the retreating stage up into two phases. Between day 150 and about day 250, water was moving as big, wide currents, and probably 2 miles deep and 1,000 miles wide, moving across the earth, kind of like the jet stream in the air. Water moving as sheets, and there was nothing to hold it back. There was little friction. It was mostly flooded still. But as more mountains and plateaus become exposed above the floodwaters are forced to go around these objects, and that's when water is moving in channels. And these are two important phases of the retreating stage because they both do different work on the surface of the earth and produce different landforms. With the channelized phase, landforms are superimposed on the sheet flow landforms. I'll be going into this more and more as I continue here. And here's that diagram. I talked about this last night. I believe that's practically when all the sediments were laid down. Now today I'm going to continue from day 150 down to day 371. And when the earth is mostly totally flooded, water is moving as sheet. When the water, whoops, went the wrong way. Yeah. And when the water, towards the end, it's more channelized. Now, at day 150, I believe there was, and I've done a number of calculations on the amount of erosion, by the way. I will be telling you about this. But at day 150, I believe we had a lot more sediments and sedimentary rocks on the continents. And then the retreating stage eroded this off for 221 days, and this is the current surface of the continent. Thick sedimentary rocks. The average thickness is said to be a mile, but I think it's more than that. I've looked at some recent numbers. I think it's probably 2 or 3 miles. There are some basins on the surface of the earth that have 20 miles of sediments in it. The thickest sediments in the world are in the South Caspian Basin, which is kind of a circular-shaped basin, 600 kilometers in diameter, that has up to 28 kilometers of sediments in it. And by the way, it's dated as practically all Cenozoic. Now, erosion on a million-year time scale is rapid. Like I said, you can flatten all of North America down in a minimum of 10 million years and a maximum of about 50 million. But on a 1,000-year time scale, we can go to the regular statistics in areas that are different terrain, mountainous, rough or smooth, and high-low precipitation, and get the average erosion. This is the average over a 5,000-year period. Now, this does not include, these are big, broad-scale averages, by the way. They do not include areas that have rapid erosion, like landslide areas, glaciated areas, this sort of thing. But you could see on this, in 5,000 years, high precipitation and mountainous, sort of like the Cascade Mountains here, that 7 feet of erosion has been the average in 5,000 years. What is this telling us? This is telling us that in 5,000 years there has not been enough erosion to erase the surface features of the floodwaters running off the continent. So we should see the evidence of the runoff on the surface of the continents if the flood was a real event. And this is in the subfield of geomorphology, or a subfield of geology. And indeed we do. In fact, geomorphology, I found it as a gold mine for creationists. And this is a summary. This is just a snapshot of the research I've been doing in this area for the last 20 years. So let's get into the main issues. How did the floodwaters drain off the continents? Oops, I can see I have 2 slides that are, but here's the big picture. Sheet flow at this time, and the continents are rising up. I noticed I had X'd out on this as I went through this. Psalm 104, verses 6 to 9, where it says that thou coverest the mountains with the deep, and at thy command the floodwaters drained. The mountains rose, the valleys sank down, and then God set a boundary that the floodwaters may not pass over. Psalm 104, verse 8, the best translation is American Standard Version, which says the mountains rise, the valleys sink down. And when that happens, that's differential vertical tectonics. Tectonics is the shifting of the crust of the earth, either vertically or horizontally. So with shifting like that, the waters are going to drain from off the higher areas going up, down into the lower areas going down. So this is the big picture of that. In the western U.S., the areas coming up, and the waters that were normally going generally from west to east split. And you have half going into the Mississippi and the other half going to the Pacific. And sometimes they're moving at high speeds. We put some numbers on this. I think I will have those numbers in here. See, this is a very abbreviated talk. I have actually 2 hours of talks on this, and it's down to 1. So at this point, I can't remember exactly precisely what slides I have coming up. So is there evidence that the mountains rose and the valley sank down? Yes, there is indeed. It's a theme all over the earth, even on the bottom of the ocean. For instance, the Beartooth Mountains are granite as well as the Bighorn Mountains. This pattern is granite as well as this pattern right here. And the Beartooth Mountains are up to 13,000 feet above sea level. And they're mostly a granite with some patches of sedimentary rocks at the top, Beartooth Butte. Bighorn Mountains, the same way. But the granite in the Bighorn Basin is 10,000 feet below sea level. And the greatest change is right here at the Beartooth Fault, along the edge of the Beartooth Mountain, where the Beartooth Mountains went up or the Bighorn Basin went down 23,000 feet. In the northern Bighorn Basin, the southern Bighorn Basin, the sediments go down to 20,000 feet below sea level. Here are some of the figures from the literature, but first a geography lesson. Wyoming is the best place to see this. First of all, there's not a lot of biology on the surface, so you can see the rocks, not like doing geology in this area. And so Wyoming is a series of mountain ranges, mostly granite, and then basins where the granite is sunk down and filled with sedimentary rocks. And here are some of the Wind River Mountains are the largest. They're up to 14,000 feet. Where that calculation was made just previously is the northern Beartooth right in there. But you can do this calculation in the Wind River Basin, Wind River Mountains, and here's the Hanna Basin, and so forth. And the figures from the literature are this, where the granite, which is the upper crust, which is probably level at day 150 over Wyoming, it's changed like this, where the granite went up and some granite went down. You can see the numbers there. Various mountain ranges and the depth. Now the biggest change, the largest change, is the Wind River Mountains, where the granite is up to 14,000 feet. But in the Hanna Basin, it's down to 31,000 feet below sea level. That represents a change of 45,000 feet of this going on in Wyoming. You can make similar calculations for many other places, like the Uinta Mountains. I've done that. It's about 40 to 45,000 feet of this. And then critics challenge us with, well, how are the floodwaters going to cover Mount Everest? You know, but Mount Everest doesn't have to be covered by the floodwaters. Mount Everest comes up out of the floodwaters, you see. Psalm 104:8, the mountains rise, the valleys sink down at God's command to drain the floodwaters off the land. And by the way, some people think that Psalm 104 is a creation psalm and that verses 6 to 9 apply to creation. But verse 6 indicates that God covered the mountains. The only other time that the earth was covered by water is on day 2 and day 3. And that's what some people, theologians, think that this refers to. But day 2 and 3 is an uncovering of the mountains, you see. Uncovering. Well, in Psalm 104, it's a covering of the mountains. So it's definitely referring to the flood. And verse 9 says that God set a boundary that the oceans may never cross over to cover the earth. So Psalm 104 refers to the flood. And to drain the floodwaters, mountains go up and the valleys sink down. Now, some versions of the Bible have it a little different, that verse, but the New American Standard Version is the proper way to translate that. And I believe this is what happened at the mountains and valley level also occurred at the bigger scale, where the continents come up and the ocean basins sink. Here at day 150, everything was flooded, so the future continents were heading up and the future ocean basins are coming down. Do we have evidence for this? Actually, tremendous evidence of the water flowing off the land, which will be the rest of the talk. But I want to focus for a short time on evidence that the ocean basins have sunk. What is some of that evidence? Some of the evidence is along the continental margin, where you have thick sedimentary rocks along the continental margin, the continental shelf, the continental slope, and the continental rise. There are huge basins, like off the east coast, and there's sedimentary rocks up to about 20 kilometers thick off the east coast of the U.S., and they cover big basins that have sunk. They know that these have sunk to make room for the sediments, while the Appalachian Mountains have gone up. This is what the literature says for the eastern United States and the continental shelf. But out in the deep ocean, we have these really strange volcanic mountains that are flat-topped, called guyots. And both the creationists and evolutionists agree they were generally truncated near sea level. We would have them truncated by fast currents during the flood. They think it was done over hundreds of thousands of years when it was near the sea surface. But regardless, the average depth of a guyot now is 5,000 feet below sea level. Planed off near sea level, flattened by fast currents during the flood, and now the ocean basins have sunk at an average of 5,000 feet. And this is admitted by a number of geomorphologists that say that this is evidence that the ocean basins have sunk. I think I have a quote. Lester King, in a provocative book called Wandering Continents and Spreading Seafloors on an Expanding Earth, he is a world traveler and a geomorphologist, and he's been all over the world. I have some more quotes by him. He said this about guyots. And not only guyots sinking, but also the land adjacent on the continents rising. He says notice the adjectives he uses. The fundamental tectonic movement of global geology. Notice this is global geology. Are vertical. We obviously see vertical tectonics everywhere, even on the ocean bottoms. They're called abyssal hills, where the hills have come up and the troughs between the hills have sunk. 90% of the ocean bottom below the sediments are abyssal hills, and they show differential vertical tectonics. So the fundamental tectonic movement of global geology are vertical, up or down. Every part of the globe, on the continents or in the ocean basins, provides indirect evidence? No, direct geological evidence that formerly it stood at different levels, up or down. Most scientists can't write. This is poor writing. What he's essentially saying is that we know that in the past that the level of the land, the crust, has been at different levels, and now it's either up or down from that level. So, and it's like this on the continents and on the ocean basins. This is powerful evidence of Psalm 104:8, that where the mountains rise and the valleys sink down, and draining the floodwaters in the process. As he says here, there has been repeated tectonic episodes, always in the same sense. The land goes up, the seafloor goes down. That's almost a direct quote of Psalm 104:8 by, I'm sure he's not a Christian. So, interesting. Also, as the land was coming up and the ocean basin sinking, the water's going to come off the land, sometimes at high speeds. If there's no mountains in front of the currents, there's nothing going to stop it from moving at high rates. When you have mountains popping up in front of it, it's going to act like a brake and cause a lot of friction and slowing of the currents. So a huge erosion would be expected as the floodwaters eroded off. And you see this in a number of areas, eroded ridges and cliffs. For instance, the Blue Ridge, along the Blue Ridge Mountains, there's an escarpment along there, and it's an erosional escarpment. Along the coast of continents, especially like around South Africa, you have a huge escarpment where it's been eroded. It hasn't been folded up, and shows erosion of thousands of feet of sediments along the coastal areas. And also erosional remnants on land. I'll get into this a little more. But I did a calculation of the amount of erosion over the Colorado Plateau. One area is called the San Rafael Swell in central Utah. And just by trigonometry, you can calculate the amount of erosion over Price, Utah, or Helper, Utah. The strata, see, here's the San Rafael Swell. It's like a bowing up of the sediments. And as they're bowing up, it got eroded, mainly in the middle. And then on the edges, you have tilted sedimentary rocks. And on the north limb, here's the sedimentary rocks right here tilted. And even when you, north of the area eroded, you showed about 600 meters of erosion. So when you add up the angle of dip, which is about 8 degrees, and the distance here, just by trigonometry, you get an average erosion over this area of 4,200 to 5,100 meters. That's up to 17,000 feet of erosion over the San Rafael Swell. And that's typical of the Colorado Plateau. The Colorado Plateau is 150,000 square miles. And from the literature, a guy named Schmidt in the journal Earth Surface Processes and Landforms says, taken overall, the mean thickness of the sedimentary cover removed from the Colorado Plateau lies between 2,500 and 5,000 meters, which in feet is 8,200 to 16,400 feet. That's the average erosion over the Colorado Plateau. And this is not unusual for lots of other areas. I did a calculation that is now being published in the Creation Research Society Quarterly on the amount of erosion over the Appalachians. There's a number of ways to do this calculation, and I got approximately 20,000 feet of erosion over the Appalachians. It had 20,000 feet of more sedimentary rocks on it before the Appalachians rose up out of the floodwaters. Here's a few numbers just from the literature. 6,500 feet in the Rocky Mountains and foothills of southern Canada. And this is from the literature. I found that number pretty close. 21,000 feet in the Appalachians, 20,000 feet in the Flinders Range, South Australia, 10,000 feet in the Welsh Mountains of the United Kingdom, 5,000 feet in southeast England, and 8,000 feet in southern Africa. So the continents are greatly eroded, exactly what we expect during the flood, during the retreating stage. It's showing the tremendous erosion. Now, when you erode an area, you don't usually erode everything. A lot of times, if the erosion is quick, like in a flash flood, you have erosional remnants, like in this flash flood in a field in South Africa. It left erosional remnants. Oops. Wrong button. See, it eroded this part right in here, but it left a number of erosional remnants. That's typical of floods. And when you have a quick flash flood, you know something? We have a lot of erosional remnants on the continents. Like Devil's Tower is my favorite erosional remnants. This is the throat of a volcano, where the lava was coming up like this in a conduit. Now that, and then it spread out as the volcano, probably way up here. The volcano was a cone right up here during the flood, and this was the lava coming up. Now lava doesn't come up through air and end up with a circular feature. It's obvious that the sedimentary rocks covered Devil's Tower at one time. Devil's Tower is 1,200 feet above the plains approximately. Right in here. So this implies that the sedimentary rocks in this part of Wyoming were at least up to this high. Now the literature says it was probably up about this high, about somewhere in the neighborhood of 8,000 feet high. I don't know where they got that calculation. I'm going to just stick with what we know, at least was at the top of Devil's Tower. And Devil's Tower, if you look at it closely, is like a basalt. It is similar to a basalt. It has lots of columns. Now, in those columns, you're going to absorb a lot of water and freeze it, and it's going to knock that thing down to blocks by freeze-thaw weathering in a very short time. Devil's Tower shouldn't last more than tens of thousands of years at the most. But the literature used to say, they used to have a big sign there saying that the sediments of the plains were at this level 40 million years ago. So in 40 million years, it all eroded down like this. Well, Devil's Tower hardly erodes at all. In fact, the width of Devil's Tower has not changed much since the beginning. They've changed that sign. Luckily, I got some pictures at the time. Now they say, well, it's only been there 1 or 2 million years. Oh, well, that means the plains eroded in 1 to 2 million years? So they can't have it both ways, you see. So they have a real problem on this. Now, I had an artist draw. What would you expect Devil's Tower to be like if it's erosion by slow processes over millions of years? That's called uniformitarianism, uniform processes, gradual processes, and it's going to take millions of years. And it would if it was true. So what would Devil's Tower look like? Devil's Tower, remember, by freeze-thaw weathering, would crumble. And by the way, vertical surfaces erode a lot faster than horizontal surfaces, because you've got block falls and landslides. So as the plains are eroding, this is what Devil's Tower should look like if uniformitarianism were true. It just should be a pile of blocks as the sedimentary rocks are removed from northeast Wyoming. And that's what Devil's Tower should look like right now. But in the creationist scenario, during the flood, it was a volcano going off. And it's the throat of a volcano. And for some reason, it stopped and became harder than the sedimentary rocks, and for some reason was not eroded. Remember, floods leave erosional remnants. Why? Maybe because the currents were a little bit slower there, or maybe because it was harder. I don't really know. But as the sediments are eroded all around it, and the volcanism goes, it just leaves the tower hanging there. So that's what you'd expect during the flood, leaving an erosional remnant with a little bit of debris around it, indicating that it's not that old. That's what we expect during the flood model. And there's lots of erosional remnants around the area, and this is a famous one. If you've never been there, I'm sure you've seen this in a lot of cowboy movies. They seem to film a lot of cowboy movies around Monument Valley, excuse me. Anyway, those monuments are sticking up about 1,000 feet, and they're capped generally with sandstone, but that sandstone is pretty soft. You can go to the same sandstone nearby and rub it with your hands and it flakes off. They're about 1,000 feet, and it's just flat around there, showing there's no drainage patterns that I know of, and it's in a very wide valley. And this area had to be, you can connect the strata across the valley. So the only way you can have a pattern like this, because if it's slow erosion over millions of years, these would not be left standing at all. In tens of thousands of years, they would erode with the area around it. The fact that they're hanging vertical 1,000 feet indicates rapid erosion of the continents. And of course, here's another erosional remnant. This is another throat of a volcano. It's Shiprock, New Mexico. It's 1,700 feet above the flat bottom of the large valley. So with all this erosion, I'd say maybe an average on the continents of maybe 8,000 feet. Where did all this material go? Well, as the continents are coming up, it's going to be coming off the continents, and it's going to be depositing where the currents slow down, and that's going to be where the currents hit deeper water, and that's going to be on the edge of the continents. See, the continents are coming up, but the edge of the continents are sinking. We have lots of evidence of rapid sinking in big basins filled with sedimentary rocks along the edge of the continent. Indeed, that's what happened. The continental margin is a mysterious feature. This is where the sediments would pile up as a sheet, because it's sheet flow running off. I'm still in the sheet flow phase, and it's going to be deposited as a sheet. And the continental shelf is a sheet of sediments all around all the continents and larger islands. And this sheet is interesting in that on the continental shelf, it's very shallow and it only deepens very slightly going out. And some continental shelves are hundreds of miles wide. And all this is sedimentary rocks that have come from the continents. And then when you get to the edge of the continental shelf, you have a drop-off called the continental slope. And then it gradually changes slope and smooths out to the continental rise. Right here is the shape of it with an exaggeration of 50 to 1, like that. This is what it looks like without any exaggeration. But the continental shelves are mysterious features because most currents that deposit sediments along the edge of the continents go parallel with the continents. And so any sediments coming from a river delta should be spread out and then sloughed down to the deep sea through what's called mass movement. So we should not have a profile of the rocks going way out 100 miles or so and then dropping off. This is a very unusual profile, and I believe it's evidence of the sheet deposition during the erosion during the flood depositing the continental shelf. And Lester King believes this is indeed the case. He says, here's the problem about the continental margins. Briefly, the continental shelf is too wide, and towards the outer edge is too deep to have been controlled by normal wind-generated waves of the ocean surface. The wind controls the average currents of the ocean. We would not expect this if the continental shelf sediments were deposited slowly over millions of years. I see this as strong evidence for the runoff of the floodwaters and the deposition of that erosion from the continents. In summary, of sheet erosion of the continents and sheet deposition, continental erosional remnants are evidence for rapid sheet erosion. The continental shelves provide evidence for rapid sheet deposition along the edges of the continents, not slow processes over millions of years. What we see on the continents is strong evidence against those millions of years. The third topic. When water is moving off at high speeds on the continent, it has lots of debris in the bottom of it, and it's moving along, and then that debris will erode the land and also tend to smooth it to a flat surface, forming what's called planation surfaces or erosion surfaces. The Dictionary of Geological Terms defines an erosion surface as such. And this is similar to a planation surface. I'm going to use the term planation surface because it's more descriptive. It's a generally flat surface. It's a land surface shaped and subdued by the action of erosion. Well, that's not too much insightful. Especially by running water. Why running water? Well, because they have these rounded rocks on the top of these erosion or planation surfaces, which I'll get into. The term is generally applied to a level or nearly level surface. In general, I refer to erosion surfaces rolling a little bit, but planation surfaces are generally flat as a pancake. And I'll get into that right now. Here's a typical small one. They're called terraces or plateaus or mesas a lot of times. Here's a little terrace near Graybull, Wyoming. You can see the dip of the sedimentary rocks. They're especially common where you see where the sedimentary rocks have been tilted and it's been flat. The top has been flattened. In this terrace, you see the sedimentary rocks dipping about 30 degrees, and these are the Bighorn Basin, this is usually this basin fill, as I call it, thousands of feet deep, is composed of alternating sands, which are harder, and then shales, which are softer. So it's alternating hard and soft rocks. But whatever flattened this didn't care whether it was soft or hard, and it flattened at the same angle. That's a planation surface. And there's rounded rocks on there, so you know that it was done by water, because only water rounds rocks, especially quartzites, which I'm going to get into soon. Now, we have evidence that planation surfaces once were much larger, and they've been eroded since they were first formed. Lester King says this about a lot of continental areas. He says, a planation of extraordinary smoothness developed over enormous areas in all the continents. These planation surfaces are found on all continents, even on Antarctica. A lot of planation surfaces are on the tops of mountains. They were once planed over a large area, and they lifted up and mostly eroded it, but a few of the mountains still retain the planation surface at the top. And the largest planation surfaces are on Africa. 60% of Africa is a planation surface called the African surface. Have you seen pictures of the Serengeti? Notice how flat that is? But if you looked at the sedimentary rocks, the strata, and even the igneous rocks below it, they're warped and twisted and folded like this. And if you project those folds up above the land, they might go up thousands of feet like this. And whatever it was just flattened it all. By the way, present processes do not create flat terrain. They destroy flat terrain. I'll get into that a little more. He says from the evidence we know that these planation surfaces were once larger. And from these large planation surfaces, all the world's present scenery has subsequently been carved by renewed erosion. Other geomorphologists said that practically all the area of the earth was a flat surface at one time in what's called the Middle Cenozoic. And then you had all this mountain building in what's called the Late Cenozoic, and it mostly eroded the planation surfaces. And I go along with that because a lot of planation surfaces are now at the tops of mountains. Now, I've been studying these things for 20 years. So in my neck of the woods, in Montana and in adjacent Canada, there are, in general, the plains, the high plains is what we generally call it, is generally 4 levels of planation surfaces, 4 levels. Probably at one time, while it was being eroded, the top level once covered the whole area, hundreds of square miles, thousands of square miles, and then it mostly got eroded, leaving a few erosional remnants of the higher level, and then forming another lower level, and doing it again and again. And this is what you see in this area right here. These are the top 2 planation surfaces in northern Montana on the high plains and adjacent Canada. The highest level is the Cypress Hills level. Has anyone ever been to the Cypress Hills? Oh, a couple of you, okay. I'll show you some pictures of it. It's about 80 miles long and 20 miles wide. And it was once continuous before it got dissected, either late in the flood by channelized erosion or post-flood during the Ice Age, or both. I think both. And this is a continuation. They had a little, this is the Swift Current Plateau. They had a little contention on whether this was connected with this, and now they think it is. Now there's a second level. The second level is actually around here and forms plateaus in northern Montana, right in here. Opime, Flaxville area. And also, here's the Continental Divide right here. There's a few of these erosional remnants east of Glacier and Waterton National Parks, right in here that are connected to this level right here, the Flaxville level. Now, look at the scale, 100 kilometers. That's approximately 60 miles, so this is large scale. This is a rose diagram because the tops of these high plateaus are capped by 75 feet of rounded rocks called quartzites, and yet these plateaus are hundreds and sometimes thousands of feet above the rivers to the north and south. Like the western Cypress Hills is 2,500 feet above the South Saskatchewan River and the Milk River. So it's a high plateau, and it's capped by rounded rocks, billions of rounded rocks on here. By the way, those rounded quartzites are all through here, but they've been reworked by glaciation. So here, let's take a look at Cypress Hills. They call it the Cypress Hills. I wish the Canadian government would rename it the Cypress Hills Planation Surface. But it's a touristy area, and no one would go to a Cypress Hills Planation area, so they got to keep the Cypress Hills. But notice the top of that is flat as a pancake. That's in the northwest part of the Cypress Hills. Now here's the central part of the Cypress Hills, still flat as a pancake, in the eastern Cypress Hills. They're east in Saskatchewan. And when you drive up on it, it reminds me of driving across Kansas, flat as a pancake. And when you go to drive to the edge of it and look down 1,000 feet to the next planation surfaces, you start to see what is capping the Cypress Hills. Conglomerate. And that conglomerate is 95% quartzite, which from paleocurrent directions originated from west of the Continental Divide, probably in central Idaho, but I'm getting ahead of myself. Let's take that. There you can see the conglomerate right there. Another close-up. And these rounded rocks are quartzite, but they have these cracks on them, semicircular cracks called percussion marks. Right there. These are caused by tremendous turbulence and banging. Percussion marks are not being formed today on quartzites, even in flash floods. I think there are powerful evidence for the powerful turbulence during the flood. Here is more quartzite. This has hundreds of percussion marks on them, right in there. Here's how I think percussion marks were formed: by fast currents moving at high speeds off the Rocky Mountains east of the Continental Divide, eroding the Cypress Hills level over a wide area, and then eroding that, leaving erosional remnants, and then eroding the Flaxville surface, and so on. The larger rocks were being carried along the bottom, forming the flat surface. And the medium to small rocks are being carried up in the current and come banging down, forming percussion marks. Based on that, Peter Kleberg of Great Falls, Montana, did a few calculations based on the surface slope, and there's a relationship between the horizontal velocity and the fall velocity, and he got numbers like this for the velocities of the material, and the minimum current depth coming off the Rocky Mountains is a sheet current. I'm still talking about sheet flow here, by the way. I haven't got to the channelized currents yet. But let's talk about a 6-inch wide bullet. This is what we estimate is the largest rock that can be carried up in the water in suspension and come crashing down. It's about that round and maybe about that long. It's the shape of a bullet. Anyway, a 6-inch wide bullet to form percussion marks on it would take a minimum current speed of 65 miles an hour and a minimum current depth of 180 feet. Now these are equations used in engineering, civil engineering. 65 miles an hour is about the speed limit of the highways in Saskatchewan and southern Alberta, and approximately 2 to 3 times the fastest flash floods on Earth that go down steep mountain slopes. What are we talking about? We're talking about powerful evidence of the runoff of the floodwaters from off the Rocky Mountains going east and eroding and moving these resistant rocks far to the east, forming planation surfaces. Now, planation surfaces, like I said, are worldwide. The best ones are in Africa. Second best ones are in Australia. You don't see a lot of them here. Go to the high plains or some of the mountain areas of the Rockies, you see the planation surfaces. This is a different area. This is mainly a depositional area, and then followed by mountains uplifting, the Olympics and the Cascades, and a lot of volcanism. Anyway, planation surfaces are found all over the Earth. Other places in Montana, the tops of the Beartooth Mountains are plain flat. This is granite. Today, there's nowhere granite is being plain flat. It's against the idea of present processes over millions of years. I mean, you see a close-up of these mountains. You can see the flatness of this granite. And they're at different levels because of faulting. There's a little fault there. In fact, this area used to be a planation surface, but has been greatly eroded afterwards by water. this was not eroded enough to make it rough like this. The Beartooth Mountains, and you see the same thing in the Wind River Mountains, flat top mountains. This is square top mountain at 11,500 feet. And to the east, you see a sedimentary mountain where the sediments are tilting like these. You can see the tilt about 50 degrees down to the west, and it's been planed off. But not every mountain's been planed off. And that's probably because it's complicated in the floodwaters. The planing was probably occurred when you had fast flow. But other areas, because of mountain rising and volcanism, slowed the floodwaters. So in other areas you form planation surfaces, in other areas you didn't. There's a lot of processes going on at the same time during the runoff of the floodwaters. Eastern Australia, above the coastal section, you have an escarpment, an erosional escarpment, where you have a cliff about 2,000, 3,000 feet, or a general cliff. Some places it's not a cliff, and it's been eroded all through there from the coast back almost 50 miles to this escarpment. Then on top of the escarpment, you have what's called the tableland. That's a planation surface that's is the width of Australia, over about 2,000 miles wide. And this is what it looks like in west central Australia. The strata are vertical here. How do you get vertical strata? Well, you have a big fold that comes up like this in the strata, like this. And then it's sheared off like that. And what's left is vertical tilted sedimentary rocks. You see a lot of vertical sedimentary rocks here and there in the Western Rockies. And water planed it off to a nearly flat surface, but it has a few rolling hills. So in summary, if it was slow erosion over millions of years, this is what we should expect everywhere. There should be no planation surfaces at all because they're not forming today. Now this example will be in tilted sedimentary rocks. They're the easiest to see. Hard sedimentary rocks should be left as ridges, and softer sedimentary rocks should be eroded, and some of the eroded material should fill up the valley. That's what we should see everywhere, but we commonly see this. Both hard and soft rocks are sheared off and truncated the same, leaving a capping of rounded rocks by water. Powerful evidence of the runoff of the floodwaters off the land, forming flat surfaces that are not forming today by present processes. Now I'm going to shift gears. And this is what we observed. Here's a planation surface in north central Montana. This is so flat that they built an airport to the left there that you can't see, but it's being destroyed by present processes of erosion from a river or stream coming from the Little Rocky Mountains. Present processes are destroying these flat surfaces. They're not forming them. So there's a big problem in uniformitarianism, and they're worldwide, again indicating a worldwide flood. In summary, of planation surfaces are common as erosional remnants, which means they were once much larger. They're worldwide, and they're difficult, I'd say impossible, but I'm just going to be conservative and say difficult to explain by slow processes over millions of years model. That's the secular way, the mainstream geological explanation of geology. Now, the fourth topic, resistant rocks carried hundreds of miles from their source. Quartzite rocks, now I'm going to focus mainly on the northern Rockies. I've done research in the Alaska Range and the Appalachians, and from the literature, South Central Asia. We're finding similar themes. But anyway, here's the big picture. Generally west to east currents, and the mountains are coming up, and as you're coming up into a fast current, and the current is forming planation surfaces, and it's eroding the mountains coming up. And the resistant rocks are carried long distances, and they go further and further away. They get smaller and smaller because they bang into each other and they break, and the edges get rounded off. You can round a rock generally in 20 miles in a stream, so you round these rocks pretty fast in water that's moving, and the faster it's moving, the faster you're going to round them. But anyway, this is the big picture. Early in the sheet flow phase, but with time, the Rockies become exposed above the floodwaters, splitting the waters, and the water is then forced to move towards the Pacific or towards the Gulf of Mexico. or into Canada that will end up in the Atlantic. So that's the big picture. So you're going to have resistant rocks from the Rockies carried both west and east of the divide. So I've been examining these things for 20 years all over Washington, Oregon, Wyoming, Saskatchewan. This is generally where the quartzites come from. Now, quartzite is a metamorphic rock. It was a sand and absorbed maybe 30% of its volume as cement, which is a very big problem in the uniformitarian model. How do you get all that cement in the sand? And then it becomes a sandstone. Then you heat it up a little bit because it was deeply buried in this area, and it's come up after it was buried. And you heat it up, and you recrystallize the sand, which is mostly silicon dioxide, like the glass in this window, and you fill up the pores to the point where it's a non-porous rock. And it's hard and dense, and it's one of the hardest rocks there is quartzite. It's a metamorphic sandstone. And it's generally found in this area of the Rocky Mountains. That's where you find it. You find patches of it in here, but the majority of it's found from central Idaho, northern Idaho, extreme western Montana. So that's where the quartzite is mostly found, as big sheets, big layers that look like sedimentary rocks, but they've been heated up and they're metamorphic rocks. It's part of what's called the belt supergroup. And here's where we find them west of the continental divide. Now, the green triangles are small areas, quartzite areas, and these quartzites have been transported and rounded. These are rounded rocks by water. They're sometimes this big, sometimes that big, and it varies. And the larger green areas are larger areas of quartzite. But you can see from this that you find them all through in here, on top of the Wallowa Mountains. Here it's on top of the Blue Mountains. And you find it all through the Columbia Gorge, and you find it on all the lava ridges around Yakima, up to 4,000 feet on the Horse Heaven Hills. And you find it clear to the Columbia River. And by the way, this area has been glaciated clear down to Olympia, Washington. And before it was glaciated, the quartzites were even in there. They were spread several mountain ranges from the nearest source of quartzite, which in this area would be up in here. That's the nearest source of quartzite. And yet you find them in here. I verified this at a number of places. Practically every place I look, the glaciers have reworked it and mixed it up. And about 1 out of 200 rocks is a rounded quartzite that come from well to the east. And some of them still have percussion marks on them. So I verified this in about 8, 9 different places north of here, around Everett, Camino Island, the Stillaguamish River, Jim Creek, number of places. The most interesting places are on top of the mountains, right in here. And that's the top of the Wallowa Mountains. Have a number of these quartzite locations at the very tops of the mountain. And here's one of them, 8,200 feet, near Lookout Mountain. And here's the largest rock transported from 100 miles to the east. That weighs about 400 pounds. I was hoping to bring that back. We had this is a big creationist group, and we have a lot of fun getting out and doing this. We had 8 horses with us. I was hoping the horses would take this back, but I was told that no way are they going to do that. First of all, they couldn't get the horses up on the ridge. So how are we going to get it down to pack it on a horse? But they said no horse is going to carry that out. But notice how well-rounded it is from water action. It's so rounded, it's almost polished and smooth. And here are the quartzites on the top of what's called Gold Butte in the central Blue Mountains, north of Burns, about 5,500 feet. Now, they call it Gold Butte because there's gold within the finer particles within in the quartzite gravels. There's gold. In fact, on the top of the Wallowa Mountains, they had a placer gold mine for many years until it became a wilderness area and they had to close it down. Gold was transported also with these quartzites, hundreds of miles from Central Oregon's the nearest source. This is about 250 miles from the nearest source right here. I showed you that map, and I'm showing you this again because the tops of these plateaus are capped by quartzites, like the Cypress Hills averages 75 feet of quartzites capping these things, these mountains. But you go into Saskatchewan, below the glacial debris, you find quartzites in this blue area here. Here's Saskatoon, Regina, Prince Albert's right in here. And then you have it in southwest Manitoba and adjacent North Dakota. The farthest distance this has been transported, by the way, quartzite doesn't outcrop on the plains. The nearest area where this comes is from central Idaho. This is a transport of 800 miles across the Continental Divide, from west of the Continental Divide east. No current rivers are going to do such a thing. Again, powerful evidence of the floodwaters carrying the resistant rocks long distances. Now let's go to southwest Montana, adjacent Wyoming. We have some interesting features here. We have quartzites on tops of mountains. We have quartzite rocks, rounded quartzites, piled up thick in some huge cracks. For instance, I've been to many of these places, by the way, to verify them. East and northeast of Jackson, Wyoming, there's a huge area of quartzites up to into south central Yellowstone Park near Yellowstone Lake. And that's up to 11,000 feet deep, where they piled up rounded rocks, piled up 11,000 feet deep. They form the tops of some of the mountains now, and the top's been eroded off. So it was once deeper than 11,000. Here in Idaho, this huge area is 15,000 feet deep. And here's other large areas. Right in here, they're on top of the Teton Mountains. Me and Brent Carter took a 3-day hike up to the top of Red Mountain in the northern Teton Mountains to find. We heard this from the literature that there's rounded quartzites on the top of the Tetons. So sure enough, there we are. There he is on the top of Red Mountain, 10,000 feet in the northern Tetons. And there are some of the rounded quartzite rocks right in here. Some have been split perpendicular, probably due to frost action. And you can see, here's the texture of the quartzites, by the way. They've been recrystallized, and they're sort of glassy or vitreous. That's the typical quartzite texture right there. And this is the largest one we found on the Teton Mountains. It's about 20 inches. Notice how well-rounded it is by water action. So what are we talking about? Erosion from the western Rocky Mountains carried up to 800 miles to the east, 400 miles to the west of the Pacific Ocean, and it was generally probably flat when they were first eroded. And then the mountains come up and carry some of the quartzites up. See, this study of quartzites is telling us a lot about tectonics during the flood, when some of the mountains came up versus when others came up. So there's a lot of offshoots to this. And on top of the Teton Mountains, we found, of course, rocks with percussion. I find percussion marks on quartzites all over the area, indicating very turbulent flow. This is on top of the Teton Mountains right here. There's your percussion mark. This is one of the hardest rocks in the world, and yet it's got all these cracks on it due to banging, hard banging, and percussion marks aren't being formed today. In summary, quartzites are spread up to 800 miles away. They're up to 15,000 feet in deep paleo cracks. Percussion marks are not forming today, and percussion marks indicate torrential flow, exactly what we expect in the runoff of the floodwaters on the surface of the land. As the floodwaters are running off, they erode, they carry the resistant rocks long distance and form planation surfaces. Now this generally is what you expect during the flood, during the sheet flow phase, when water is moving as wide currents, like a sheet, 1,000 miles wide and maybe 2 miles deep. But then as more mountains and plateaus are exposed, the water's channelizing. Now I'm shifting to the channelized phase of the flood. And it forms features on the surface of the earth on top of the sheet flow phase. One of the most common features is it forms water and wind gaps. What is a water gap and a wind gap? A water gap is a perpendicular cut through a mountain range or a plateau of which water moves from one side, flows right through the gorge to the other side. The Columbia Gorge would be a typical water gap. But it's not a very interesting water gap because that's the lowest area of the Cascade Mountains. So when supposedly eastern Washington was higher, the only outlet was through the low areas of the mountains. So that's not so interesting. The most interesting water gaps is where the water could have easily gone around the barrier and didn't. It appears that the water cut right through a high barrier when it should have easily gone around. Those are the significant water gaps, of which there's well over 1,000 of them on the surface of the earth. A wind gap is a water gap wannabe. It didn't quite cut deep enough so that water flows from one side of the mountain range to the other. It's just kind of like a saddle or pass. So only wind is passing through it. It's called a wind gap as a result. Anyway, these, I believe, formed mainly during the channelized part of the flood, water moving in channels, right in here. Well, let's take a look at one of them. The best one around where I live is the Shoshone Water Gap, west of Cody, Wyoming. Has anyone ever seen this, been to Cody, Wyoming, and noticed that gap through the mountains? A few of you. Now let's get our bearings here. Yellowstone Park is over this way, and this is the Bighorn Basin right here, where you have 10,000 or more feet of sedimentary rock, or no, it goes down to 10,000 feet below sea level. Here's the Rattlesnake Mountains right here, and they're about 2,500 feet above the plains right here. And the Shoshone River starts in southeast Yellowstone Park, moves east, and comes to these mountains. It could have easily gone around and out this way, but instead it's cutting right through the mountains, perpendicular. Why did it do that? Well, they haven't the foggiest idea, even though they have about 4 hypotheses. And when you get close to it, it's cut in hard granite that you can't really see, but it's banked by sedimentary rocks. When you drive through it, you come to Buffalo Bill Reservoir. That's about 300 feet high. But when they raised the reservoir, they had to build a dam to the south to keep the water from going out. This is where the river should have flowed, out this way. But instead, it cut through 2,500 feet through hard rock, or appeared to cut through it. Do rivers go uphill and then down? No. It's a major problem. You have a lot of water gaps in the eastern United States cut through the Appalachian Mountains. Here's one of the most famous one at Harrisburg. The Susquehanna River cuts through a number of ridges when it could have easily gone around these ridges like this, but just goes right through about 3 or 4 of them in a row before it enters Harrisburg, Pennsylvania here. Quite a few water gaps and wind gaps in the Appalachians. In fact, here's one of the most famous wind gaps, Cumberland Wind Gap, on the border of Virginia and Kentucky. And this is where the strata used to cover this whole area on this ridge. And something has eroded it a notch in it. But it wasn't deep enough for the water to go from the other side to this side right here. I'm looking west. So only wind goes through here. The most famous wind gap we have in the western United States is the Unaweep Canyon of the Uncompahgre Mountains, where it's a pass. So this used to be connected. There used to be no valley here, and something eroded this right here, or only halfway down. If it went another 50%, the Colorado River might have gone through here, but no. You have to drive up to this and then down. This is the pass right in here. So this would be classified as a wind gap. Now, when you're forming water and wind gaps during the flood, you're going from sheet flow to channelized. And when you go from sheet flow to channelized flow, you have to speed up the water, because it's like forcing water through a pipe that wide, and suddenly you narrow the pipe to like that. You have to speed up the water to get the same amount of water through there. Of course, with time, there'll be less water, of course, but if we had the same amount of water, you'd speed it up. And so you can form water gaps rapidly, probably well over 100 miles an hour. Some of the most interesting and famous water gaps in the whole world are the Zagros Mountains, which are very young mountains that rose during what's called the late Cenozoic. There's 300 water gaps in just the Zagros Mountains alone of western Iran. And they're up to 8,000 feet deep. The mountains go up to 15,000 feet. A man named Thomas Oberlander is probably the world expert on water gaps. And he has a number of hypotheses on these, but none of them you can prove. In a book called The Zagros Streams, he wrote a PhD thesis on this, here's some of the language he describes it in this book. I mean, I was laughing when I was reading this sort of thing. The Zagros drainage pattern is distinctive by virtue of its disregard of major geological obstructions, both on a general or large scale and in detail, small scale. Certain streams ignore structure completely. In other words, they don't flow down valleys like they're supposed to. They cut through the mountains, and sometimes they cut back out. Some appear to seek, and I like that, obstacles to transect. Sounds like the river has a mind of its own, and it just wants to be like some of these macho mountain climbers. I want to break through that mountain. In fact, the rivers rarely go down valleys. They go through barriers. Sometimes they go through it and back out and do it again. Normal streams don't do this. This is something that has to form during the flood. And to cut to the chase, here's how I think the flood formed them. You had either ridges coming up and mountains or water draining, or probably both. But regardless, no ridge is perfectly straight, so you have low areas and high areas. So when water's draining perpendicular during the flood, it's going to take advantage of these low areas, and it's going to funnel the water through there. And as it becomes more exposed, it's funneling through these gaps, perpendicular. And it continues, cutting a deep channel through here, and it's flowing here. Suddenly, for some reason, this gives up and doesn't erode anymore, and all the water comes through here, forming a water gap. And so at the end of the flood, this is what it looks like. The water from streams ends up flowing through the water gap, and this is left high and dry as a wannabe water gap called a wind gap. You know, water and wind gaps form during floods. In the Lake Missoula flood, we have an analog of the formation of water and wind gaps. When the waters of the Lake Missoula were going through eastern Washington, they came down into the south central Washington, and we're coming from the north. And here's Washtuknacooley. The Palouse River used to go down that into the Columbia River. Here's the Snake River about 10 miles to the south. Between was a ridge about 500 feet thick of basalt, capped by about 100 feet of silt, called the Palouse Silt. And the water broke over in about 4 places, but mainly in 2. Here, Palouse Canyon, first of all, it starts wide, and then it narrows down to a thin canyon. And after the flood, the Palouse River, instead of going down its previous course, takes a left-hand turn and goes through Palouse Canyon into the Snake River. That's a water gap formed during a flood, a major flood. This Devil's Canyon is a wind gap because it's about 90 feet high barrier there, keeping any water from in here going this way. So it's a wind gap. I was just here a few days ago taking some pictures. So this is a water gap, and this is a wind gap formed during the Lake Missoula flood. So the Genesis flood is about the only way I think you can form water and wind gaps, and there's thousands of them across the world. I can't see the time back there. Got plenty of time, okay. I must be going fast because usually I'm running out of time about right now. A 6th feature forms is what's called pediments. Pediments are planation surfaces at the foots of mountains or ridges. Peda means foot, and ment means mountain. You see these things all through the Rocky Mountains. You don't see pediments around here, so to many of you, these are probably foreign objects. But this is one near where I live. These are the beautiful tobacco root mountains, and many people, that's what you notice. But how many people notice this flat surface right here? This is a pediment. It's about 3 miles wide, 10 miles long, and it's been cut in bedrock. It's not an alluvial fan or a river terrace. It's been cut in rock, hard rock, as if these mountains came out to right here, and you just sheared off the edge of the mountains, hard rock. And when you shear it off, what does the shearing leaves behind, when the currents slow down, the rounded rocks that do the cutting of the pediment, or the shearing, or the truncation. Here's another pediment in southwest Montana, in the Ruby Valley. You can see the flatness of the pediment right here. I am looking north, and here are the sedimentary rocks of the valley right here, dipping to the east about 3 to 5 degrees. But the pediment is dipping down to the west about 3 degrees, so the angle is about 8 degrees. Right in there. Nature is not forming pediments today, or present processes are not forming pediments today. And there are thousands, if not tens of thousands, of pediments all over the earth. You see them see them in eastern, southeast California. You see them in southern Arizona. You see them all through the Rocky Mountains, on the high plains. So you see them in lots of places in the world. And here are some of the rocks capping that pediment. You can see they're rounded, and a lot of these are quartzite rocks. And no quartzite outcrops in southwest Montana at all as bedded sediments. The nearest source of these quartzites is central Idaho, meaning that the currents, the water came from upstream, going parallel to the valley, and not coming out of the mountains. All theories for pediment formation have streams coming out of the mountains, perpendicular to the mountains, and they sort of go like this, supposedly, and cut the pediment. But you don't see this happening today. It's just a hypothesis that can't be proven. In fact, there's evidence against it. Anyway, to cut to the chase, here's how I believe pediments formed during the flood. In this case, instead of water going perpendicular to a ridge, you have it going parallel to a ridge. And when you buckle sedimentary rocks, the top of them expands. And when you expand it, you crack it parallel to the ridge, forming cracks like this. And those cracks is where they're going to erode rapidly. And so the ridge is going to suddenly turn into a valley. This is very common in the mountains. You see features like this, where if you would dot the sedimentary rocks, you'd have a ridge there. So the ridge has been eroded by powerful currents. And as the currents are draining and the land's coming up, the water's channelizing down the valley at high speeds, probably over 100 miles an hour. And in the process, it's forming flat surfaces along the edge of the mountains. It's either cutting the valley fill or it's eroding the rock of the mountain along the edge. So at the end of the flood, you end up with a flat surface along the edges of the mountains called a pediment. And of course, there was a little more digging. The present valley is usually a little lower than the pediment. Now, pediments, like all these features I've been telling you, are mysteries in the uniformitarian process. And in referring to pediments, Doran, in the book Geomorphology of Desert Environments, you see a lot of these pediments in deserts, because in deserts you haven't had enough erosion, because current day erosion is destroying pediments. But the erosion is slower in a desert, so you see a lot of them in the desert. Doran says this about pediments. Pediments, they've known about these for 100 to 200 years. Pediments have long been the subject of geomorphological scrutiny. Unfortunately, the net result of this long history of study is not altogether clear or cogent, and has not produced a clear understanding of the processes responsible for pediment development. Now, I was a weather forecaster for 30 years, and I became a master of weasel words. It may rain today or it may not. And as a master of weasel words, I can tell weasel words in other people. These are weasel words for saying, we haven't got a clue how pediments form. But they don't want to tell you directly. Give us more money and we'll solve it in the future, is usually what they try to say. But the more we know about these, the less and less likely are these major problems in geomorphology going to be solved. Money isn't the answer. I believe they have the wrong paradigm. The seventh and last feature is submarine canyons. Submarine canyons are mostly formed after the sedimentary rocks have been deposited on the continental shelf by sheet deposition. You notice you have sheet erosion off the continents, and it's deposited along the edge. So once you deposit it, then the currents are channelizing more. And instead of depositing, it's eroding the sediments perpendicular to the continents. Here is a drawing from, I think, National Geographic of Monterey Canyon. These submarine canyons are like Grand Canyons. There's about 50 Grand Canyons around the world that you never see because they're offshore, perpendicular to the coast. And this one is Monterey Canyon. In fact, the title of this article is called The Grand Canyon of the Sea, or at least this caption here. Here's Monterey Canyon. In fact, it starts almost near the pier at Moss Landing. In fact, if this canyon's backing up, it won't be too long before the pier crashes into the canyon. In fact, Scripps Canyon and La Jolla Canyon off Southern California are in the same boat. They have built piers right to the edge of the submarine canyon. Some of these submarine canyons, like I say, go almost to the beach, but many of them start pretty far out on the continental shelf. But anyway, this one starts almost near the beach and comes out like this, and it's a mile deep right out in here. And it kind of meanders, and it joins the Carmel Canyon, which is very straight and likely due to a fault. When they're that straight, they're likely due to faults. But these are practically all these submarine canyons are erosional canyons. They've been eroded and not due to faults. Some have been due to faults, like Carmel Canyon, like I said. It's a mile deep and about 50 miles long. And there's, like I said, there's a couple hundred of them, submarine canyons, and they're at the deepest submarine canyon is off of northern Spain. It's about 10,000 feet deep, twice as deep as Grand Canyon. But the largest volume of material eroded is the Zemchung Canyon along the Bering Shelf, about 400 miles from land. Along the edge of the Bering Shelf, you have at least 7 major canyons. And the Zemchung is about 8,000 feet deep, and it has a larger volume eroded than Grand Canyon. And one canyon is not only as deep as Grand Canyon, but longer than Grand Canyon. That's called the Bering Canyon off the southern Bering slope. So here's how I think. By the way, they have hypotheses for these, but they have lots of difficulty trying to explain these and all the other features I've been talking to you about. But here's how I think they have formed during the flood. Sheet flow off the continent deposits the rocks in the deep area where the currents slow down, right in here, forming your continental shelf and slope. With time, the currents are channelizing, and when they channelize, they start to erode that material that they've deposited. And as it continues, it forms a cut like this, and it's a reflection of the valley and canyon on shore. It's kind of like it's telescoping the water from what is currently on shore to offshore, and it's forming a canyon. It's probably forming the canyon by the accumulation of the debris that slopes down the continental cascades down the continental slope, cutting the canyon that way. As it continues, actually the land becomes exposed like this right in here, and still telescoping it as a channelized current cutting the canyon. And after it's all over, this is what you have. A submarine canyon. The average submarine canyon is actually 3,000 feet deep and about 50 miles long. And it's usually a reflection of the valley out in here. That's why they thought that rivers once cut these, because a lot of times they're off from rivers. But a lot of them aren't off of rivers, which really threw a monkey wrench into their theories. But the flood can easily explain submarine canyons by the channelized flow off onto the continental shelf. P.J. Tulling in Geology said this about submarine canyons. At present, there are few studies of the processes by which submarine canyons are initiated and grow. and further work is needed to document how self-indenting submarine canyons form and how they interact with subaerially incised valleys. To translate that, those are generally weasel words to say that we are having a lot of difficulty explaining it. We have some ideas, and they do in this case have some lot better ideas than pediments or water gaps, but we have a lot of difficulties in our theory. In summary of this, major features of the Earth's surface can be readily explained by the retreating stage of the flood. Massive erosion leaves behind tall erosional remnants, planation surfaces, and long transported boulders. The eroded sediments form the continental shelf. Valleys, canyons, wind and water gaps, pediments, and submarine canyons form rapidly during the channelized flow. Mainstream geologists have great difficulty explaining all these features with their slow processes over millions of years model. All these features are worldwide, indicating a global flood. A global flood, not a local flood. Therefore, there is abundant evidence that receding water from Noah's flood shaped the Earth's surface. If you want to know more about it, this is the abbreviated version of a large manuscript I am working on called Flood by Design. Receding water shapes the Earth's surface. It gives you a summary of these features and more that I haven't told you about yet.